Find the support moments by using the direct stiffness method for the figure shown. Here this one is a continuous beam. At A it is on simple support, at B it is on simple support, and C also it is on some simple support, and is subjected to a point load of 100 kilonewton at a distance of 3 meter from A and 3 meter from B. The total length of the span is 6 meter with moment of inertia 2I. In span BC, it is subjected to a point load of 80 kilonewton at a distance of 1 meter from B and 3 meter from C. First, we have to find out the degree of freedom since all the supports are simple supports. Here at A, theta A is the slope. It allows the rotation of the end of the beam. Similarly, at B, it permits the rotation. At C also, it permits the rotation. Hence, the total degree of freedom is theta A, theta B, theta C. That is, degree of freedom is 3. We have to consider theta A, theta B, theta C as the redundants. Here we have to consider them as the redundants that we have to calculate. The next step is to calculate the fixed end moment in span AB and BC. In span AB, MFAB, that is the fixed end moment from end A, that one is minus WL by 8. Here W equals 100, L is 6 meter, then that is anti-clockwise, that is minus 100 into 6 by 8, that one is minus 75 kilonewton meter. Similarly, from the other end, that is MFBA, that one is again WL by 8, that one is plus 75 kilonewton meter, that is clockwise. Then in span BC, it is subjected to point load of 80 kilonewton at a distance of A equals 1 meter, B equals 3 meter. Then MFBC equals, that is anti-clockwise, WAB square by L square. W is 80 into A is 1, B is 3 divided by L square is 4 square. By simplification here we will get minus 45 kilonewton meter. MFCB, that is WAB square by L square. Here W is 80, A into A, that is 1 square into 3 divided by L square, that is 4 square. By simplification, that is 15 kilonewton meter. Here now we have to calculate the vector of the loads due to the moments at the joints A, B and C. Since we have considered theta A, theta B, theta C as the redundants, here those are the coordinates. Coordinates 1, 2, 3. PL, that is the load due to vector. The net moment at A is minus 75 kilonewton meter. At B, two spans are connected, one is BA, one is BC. Then the summation of MFBA, MFBC, that is 75 minus 45, that one is 30. At C, only one span is connected. MFCB is just now calculated, that is 15. Then the load due to, if any overhangs either at A or C, no overhangs, hence P equals 0. That is the load due to initial loads, if any. P equals the vector of P is 0. Then the next step is to calculate the stiffness matrix by applying the unit rotation at coordinates 1, 2, 3 separately. First we will apply the unit rotation at coordinate 1. By applying the unit rotation A at A or 1, coordinate 1, here we have to assume that the direction of the unit rotation is clockwise, that is theta A equals 1, by keeping all the supports as fixed support. Then due to the unit rotation applied, the deformation may take place like this. Here in span AB, the length is 6 and moment of inertia is 2I. There is no deformation in span BC. Then the stiffness matrix at stiffness element, that is K11. Here we have applied the unit rotation at 1. This one is K21, that is the unit rotation. Due to the unit rotation, the stiffness value at 2 due to the load applied at 1. Here the stiffness value at 1 due to the load applied at 1, that one is K11. That one is given by, this is near end, this is far end. That is for near end 4EI by L. By substituting the values, here moment of inertia is 2 times, hence 2 into 4 EI divided by L is 6. By simplification, that is 4 by 3 EI. Then K21 for span B to A, that is far end, 2 times EI. Here the moment of inertia is 2, hence 2 into 2 EI by 6, that is 2/3 of EI. There is no effect of the unit displacement at 1 on the coordinate 3, therefore K31 is 0. Then apply the unit rotation at coordinate 2, that is theta B equals 1 as shown in figure. Here, due to the unit rotation at coordinate 2 or at B, then the stiffness elements at 1 due to the unit rotation applied at 2, that is K12, it will undergo deformation like this. Here by considering all the ends as fixed support, K12, that one is for B, this end is far end, hence that is 2EI by L. Here the moment of inertia is 2 for span AB, therefore K12 equals 2 into K12 equals 2 into 2 EI by 6, that is 2/3 of EI. By the reciprocal theorem of deflection, Maxwell's reciprocal theorem of deflection, K12 and K21 are both are equal. Then K22, here the displacement applied at 2 is theta B equals 1. Then at 2, the stiffness value is, here there are 2 spans are connected, one is BA, one is BC. Then for both are the near ends, that is 4EI by L. For span BA, that is 4EI by L, moment of inertia is 2, hence 2 times, then that is 2 into 4EI by L. For span BC, moment of inertia is 1, that is 4EI by L, that is 4. Then by simplification, here you will get 7 by 3 times EI. Then K32, the effect of the unit rotation. This one is the far end, that is 2EI by L in span BC. Then that is K32 equals 2EI by 4. That one is by substituting the values of L and EI. Then you will get, that is K32 equals 2EI by 4, that is half EI. Now, after that we can apply the unit rotation at 3. Then theta C equals 1, that is in clockwise direction. Then due to that the deformation may take place like this. Then here the stiffness element at 1 due to the load unit rotation applied at 3, that one is 0, since no effect of the unit rotation at 3 at 1 due to the unit rotation at 3. Then K23, here it will undergo deformation at coordinate 2. This one becomes the far end for C, hence that is K equals 2EI by 4, 2EI by L, that one is 2EI by 4, that one is half EI. Then due to the unit rotation, the stiffness element at 3 due to the unit rotation applied at 3, that one is the near end, it is 4EI by L, that one is by substituting the values, here you will get the value of EI. Then here the stiffness matrix is given by, that is 4 by 3 EI, 2/3 of EI, 0, the elements are in the second row, that is 2 EI, 2/3 of EI, second element, that is in second row, second column, that is 7/3 EI, 7/3 EI, third element in second row, half EI, third row, first element, that is K31, that is 0, K32, that is third row, second column, that one is half EI, K33, that is EI. Here we know that the stiffness matrix, the redundant matrix can be found out by using the relation, that is stiffness matrix into the displacement, that equals P minus PL, where P is the load due to any overhanged supports or moment pre-existing moments. PL is the moments due to the loads applied at the coordinates 1, 2, 3, etc. Then delta equals the displacement vector is given by inverse of the stiffness matrix into the vectors of the pre-existing load minus the vector due to the load applied at the load due to the load applied, that is PL. Then here to get the values of the redundance, then here we have assumed theta A, theta B, theta C as the redundants. Here the inverse of the stiffness matrix, EI is common, EI is common in all, then inverse of EI is 1 over EI. Here we have removed 3 EI, EI by 3 as common, inverse of EI by 3 is 3 by EI. Then the elements are K11, that is 4, K12, that is 2, K13, that is 0, K21, that is 2, K22, that is 7, K23, that is 1.5, K31, that is 0, K32, 1.5, K33, that is 3. Here the inverse of this one into the matrix due to the pre-existing loads, that is 0, or vector due to the pre-existing load, the vector due to the moments at coordinates 1, 2, 3, that is minus 75, 30, 15. Then by simplification, by the inversion of the stiffness matrix, that is here after simplification we will get the values of theta A, theta B, theta C as the values of the unknowns, that is theta A equals 73.39 by EI, theta B equals minus 34.29 by EI, theta C equals 2.14 by EI. Now, by using the slope deflection equation, we have to find the final moments at the various coordinates or various points, that is MAB. MAB is 0 since that is the end support. A is on the simple support. By substituting the values, the fixed end moment is minus 75 plus 2EI by L. Here the moment of inertia is 2 times I, hence that is 4EI by L is 6. Inside the bracket 2 times theta A, that is 2 into 73.39 by EI, plus theta B, that is minus 34.29 by EI. By simplification, here you will get the end support moment at end support A, that is 0. Then at interior support B, here two spans are connected, MBA, that is MFBA, that is fixed end moment, that is positive, that is clockwise 75, plus 2EI by L. Here the length is 6, moment of inertia is 2I, hence this is 4EI by 6. Inside of the bracket 2 theta B, the near end is B, hence that is minus 2 into 34.29 by EI plus far end, that is far end is A, that is 73.39 by EI. Just now we have calculated theta A. After simplification here you will get 78.21 kilonewton meter. Then in span BC, MF BC, that is minus 45, that is anticlockwise, plus 2 EI by L. The L is 4 meter. Moment of inertia is 1 times I, that is 2 EI by 4 inside of the bracket, 2 times theta B, that is theta B is negative, hence minus 2 into 34.29 by EI plus theta C, that is far end, that is 2.14 by EI, then that equals minus 78.22 after simplification. Here by observing these two values at the joint B, the summation of MBA plus MBC must be equal to 0, or the sum of the moments at joint B must be equal to 0. Then MCB, that is also another end support. End support is on simple support. At simple support the final moment is 0. Then by substituting the values, MFCB is 15 plus 2 EI by L. The length is 4 meter. 2 moment of inertia is 1 I. Then 2 EI by 4 inside of the bracket, 2 times theta C, that is 2 into 2.14 by EI plus theta B, that is minus 34.29 by EI. Then by simplification here we will get 0. Then by using the above values of the final moments, we can easily draw the bending moment diagram. Here in span AB, it is subjected to a point load of 100 kilonewton at center. Then the support moments MAB is 0, MAB is 0, MBA, that is clockwise. By observing that is hogging, first we have to draw this reference line or datum line, and then we can mark an ordinate of 78.22 above the datum line to represent this hogging moment of 78.21 or 78.22. Both are equal, that is 78.22 kilonewton meter. Here this ordinate is 0, join these two ordinates. We have represented the hogging moment above the reference line or datum line. Here the ordinate is 0, here the ordinate is 78.22. Join these 2 points by a straight line. The variation is straight line. Then similarly at C, that is end support on simple support. End support is simple support. Then at C the bending moment is 0, that is at support. Then join these 2 points by a straight line. Here this is the support moment diagram. That one is a triangle. The ordinate at A and C are 0, at B that is 78.22. Then the simply supported beam bending moment in span AB. At supports A and B the bending moment is 0. At center, that is below the point load, the maximum bending moment is WL by 4, that is 100 into 6 by 4, that one is 150 kilonewton meter. This is the maximum ordinate at the center or below the point load. That is sagging moment, hence we can show this one as positive moment. Then in span BC, it is subjected to a point load of 80 kilonewton at a distance of 1 meter from B and 3 meter from C. The maximum bending moment below the point load, that is WAB by L, that is 80 into 1 into 3 by 4, that one is 60 kilonewton meter. At the support the bending moment is 0. Then the simply supported beam bending moment is like this. By overlapping, here you will get the net bending moment diagram shown by the shaded line. Here at support the bending moment is hogging. At the center